Okay, so today we are going to talk about 4.8, which has to do with taking the knowledge we already have about finding area between two curves and knowing that area is two-dimensional, and then thinking of the area between two curves as the base of a region that is in 3 dimensions. Okay, so we are basically taking something that we already know and putting it into a new dimension, which is cool, and also requires us to think a lot about 3D shapes and what those look like. So pictures in this are super, super important, okay? So let's get started. Part 1, volume of a solid with square rectangle cross sections perpendicular to the x-axis. So at this point, we've become comfortable finding the area between two curves, which we can do using a definite integral. And again, area is 2D. We can see what we are finding the area of when we draw a picture that shows the area between the two curves that we are trying to solve for. Today, we're going to do something even more interesting and find the volume of shapes, volume 3D, where the base of said shape is defined in some way by the area between two curves. So essentially, we're taking our knowledge of finding the area between two curves and taking it further into the 3rd dimension. Ooh, ah. So this means that we're going to have to be comfortable drawing 3D shapes. And honestly, we're just going to kind of jump right into this with an example. So, for instance, what is the volume of the shape whose base is defined as the area between the curve y equals 6 and y equals 4 times the natural log of 3 minus x between x equals 0 and x equals 2? We can easily draw the area in 2 dimensions, but what we are going to do now is imagine that the area is actually the base of a 3D shape. So first I'm going to draw the area, and that's going to be over here, small in the corner. So we know that we are dealing with the area between the curve y equals 6, which I'm going to put in yellow. Y equals 6, just pretend that's 6. I didn't label my axis. And then our other line is y equals 4 times the natural log of 3 minus x. And I've already looked up the graph of this function, so you can look that up on your calculator, but I know that it roughly looks like this. So I'm going to label this guy as y equals 4 ln 3 minus x. Okay, and we know we are talking about the area between x equals 0 and x equals 2. So x equals 0 is right here, and x equals 2, let's put right there. And so our area is going to be shaded in red right here. And so before, we talked about finding the area of that red shaded region. Now, we are going to think about finding the area of a 3D shape that we need to imagine whose base is that red shaded area. So I'm going to draw a little bit of like a tilted axis here. And hopefully you can imagine this as 3D a little bit. So this is X and this is Y. And I have my line Y equals 6 up here. And I have my other line Y equals 4 ln of 3 minus x right here. And then again, I'm talking between 0 and 2. So here's 0 and here's 2. And so again, I'm actually not going to draw that line all the way down. So we'll just put 0 and 2. So the region is right here. Okay, so there is the base of the 3D shape that we are going to create, okay? And to find the volume of the solid, what we're going to do is we're going to draw little square cross sections from the base of this solid, okay? So I'm going to actually erase that red so I can start to draw little square cross sections that come up from this shape. So right here, here would be the base, and then I'm going to draw a nice little square coming up like this. Okay, and then let's go down here. Here's our base, and then we would have a nice little square cross section coming up like this. And then again, here's our base, and then a big square cross section coming up right here. That one's more of a rectangle. I'm going to redo that one a little bit. So there's our base, and then a square coming up like that. And then here's our last base right here. We're gonna draw a big square right there. So hopefully you can kind of see that this makes like almost like a little cornucopia type thing. I think that's the right word. And to find the volume, we are going to make these little square cross sections, but we're going to make these little square cross sections 3D. So what I'm going to do is I'm going to erase my drawing. Hopefully you saw that 3D figure at least a little bit. So I'm going to erase my drawing, and now I'm going to just draw one of the small red 3D boxes, right? So we're going to have, this is our base, and then our square comes up right here. And instead of thinking about this as a square, we're now going to think about this as a little bit of a cube. So we're going to add a little bit of depth. So hopefully you see here that we have this little 3D box, okay? And if you think about it, we're going to have a bunch of cross sections, so we can kind of stack these little 3D boxes together to create the volume of our large cornucopia type shape, okay? So to find the volume of the solid, the giant red thing that I drew earlier, to find volume of solid, we are going to sum the small pieces. So those small red 3D pieces, we are going to stack a bunch of them together until we create the large 3D shape. And if we can sum up the volume of each of those small pieces, then hopefully you can see intuitively that we would have the volume of the big large shape, okay? So we know that volume is equal to area times depth. So the depth of our little small 3D shapes are going to be called dx. So dx, as you might be starting to think about integration and how that might play into this, dx we know we need for the variable of integration, right? And so if we think about this, we just now need the area. So we know that depth is going to be dx. So the thing that we are missing is the area. Okay, so now let's think about our cross sections. Cross sections, and we know that they're squares. And further, we know that when we have a square, the base is equal to the height. Base is equal to, where did my pencil go? Height. And so now let's look at the base of our square, right? So we can look at it, and here is the base of our square. It is the area, or the line that goes from the top curve to your bottom curve. So the base is equal to top minus bottom, something that we are already familiar with, okay? So our top function is y equals 6. Our bottom function is 4 ln of 3 minus x. And so we know that the base is equal to the height is equal to top minus bottom, which is 6 minus natural log of 4, minus 6 minus 4 natural log, sorry, I forgot the function, 4 natural log of 3 minus x, okay? So the overall area of the square would therefore be equal to base times height, which is the same thing, which is top minus bottom. So we know that the overall, I don't know why this isn't erasing for me, area is equal to 6 minus 4 ln of 3 minus x times 6 minus 4 ln of 3 minus x, or 6 minus 4 of ln of 3 minus x quantity squared. So that is the area of one of the faces of this little 3D shape that we have drawn. So if I look here, here's a shaded face, and that area represents the face. But again, we want to be 3D. So let's think back to volume, okay? Depth is dx, so if we multiply by dx, we have created a 3D shape. So we're going to take our area, which is 6 minus 4 ln of 3 minus x, quantity squared, times dx. And now we have the volume of this little red box that we have. And now, if we want to sum up the entire volume of this 3D shape, then we could take the integral from 0 to 2, because we know our function or our region starts at 0 and ends at 2, of the volume, which we determined to be 6 minus 4 ln of 3 minus x, quantity squared, dx. Okay, and that is approximately 26.27. Okay, so what we have done here is we have summed up each of our little red boxes. Okay, so there's only one drawn here, but we can think about this as there's going to be many, many, many that, you know, mesh together to create that big 3D shape that we started with. And then by taking the integral from, you know, wherever your left bound is to the end of your region and summing up the volume of all these tiny little boxes that you're drawing, you can find the volume of these 3D shapes. And again, the hardest part of this is visualizing it. So take a second, think about it. We're going to do some more examples, and hopefully you can kind of picture this in your head. It is hard to see though, so don't give up if you don't initially see it. I will try to draw a picture different ways so you can see it. Yeah, so let me go ahead and clear that, and we can go ahead and move on to the next part of the notes. And I'm not really sure why my Apple Pencil is acting up a little bit and not deleting my previous writing, but I definitely don't need any of that picture anymore. Go away. Pause, share, resume share. Let's see here. Okay, so although these large 3D shapes may be intimidating at first glance, we can find the area using integration techniques that we are already familiar with. All we have to do is break up our shape into small pieces that have a bit of depth to them, find the volume of that small piece, and then sum up the volume of all the different pieces. And then further, we know volume is equal to depth times area. Depth is dx. Area of one of our base of one of the faces of our square cross section is equal to base times height. So the length of the base is going to be the difference between our two functions, top minus bottom, and the height. So when we are working with squares, the height is the same as the base. When we are working with rectangles, one of the dimensions, usually height, will be given, and we can figure out the other dimension using top minus bottom. And in order to sum up all of the volumes, we can use a definite integral, and then simply evaluate our integral to find the volume of the shape. And since these are pretty ugly intervals to evaluate by hand, we can use our calculators. So definite integrals on the TI-84. Hopefully you have yours with you. You can hit the math button. The 9th choice is definite integrals. So on newer calculators, you can see the integral and type in your bounds and the integrand and dx. On older calculators, enter the integrand. So that's the function you're integrating. So then comma, the variable of integration. So then you would put x or y, usually x, so comma, lower limit of integration, which would be like 0 to 2 or whatever it is. And remember to put those commas in there and close your parentheses. And the TI-84 only does definite integrals, so no indefinite integrals. But this is something that I think you have all earned the knowledge to know. Yeah, so let's do some practice. I'm going to do a couple of these, and then I'm going to let you guys do the other two, and we will talk about them in class. So first up, let f of x equals x minus 2 quantity squared, and g of x equal 4 minus x. Let R be the region enclosed by the graphs of f and g. Region R is the base of a solid. For each x value, the cross-section of a solid taken perpendicular to the x-axis is a rectangle whose base lies in R and whose height is 4 minus x. What is the volume of the solid? So first things first, I'm going to draw a picture. So I know that x minus 2 quantity squared is a parabola. That's, oh, I should do this in a different color, is going to be a parabola, and I'm going to draw that in blue. So this is going to be x minus 2 quantity squared. And then I know 4 minus x is a good old line, and I'm going to draw that like this. 4 minus x. And so now I know that region R is this region right here between F and G. But again, I'm not going to leave that shaded because I want to be able to sketch out my rectangular cross sections. So the base is always, or the area between two regions is always the base of your solids. So that's always going to be the base. And then I'm going to imagine, all right, these big 3D rectangles coming up kind of like this. So this one would be bigger, kind of like that. And then this one would be like that. Okay, so I'm going to sketch a few rectangles so I can get an idea of what that looks like. And now I need to know the area of a rectangle. So area of rectangle. And that is going to be base times height. Okay, so if I look at one of these rectangles, the base is right here, and that base is going to be top minus bottom. And so top minus bottom in this case is going to be 4 minus x minus 2 quantity squared. So I'm going to FOIL out x minus 2 quantity squared. So I'm going to get 4 minus x squared minus 4x plus 4, and that's going to be 4 minus x squared plus 4x minus 4. Going to distribute that negative, and that leaves me with negative x squared plus 3x as my simplified base. And then height, negative x squared plus 3x. And I'm going to erase that for the sake of space. And then my height is given to me in the problem since it's a rectangle, and that is going to be 4 minus x. So I know that the area of my rectangle is going to be negative x squared plus 3x times 4 minus x. And then I'm going to imagine these rectangles as having a little bit of width because they are 3D. So I know that the volume would be negative x squared plus 3x times 4 minus x dx. And then to sum up all of the little 3D rectangles, I'm going to take the integral from, I know that this point is 0 and this point is 3. And again, I found that by setting the two functions equal to each other and solving for the intercepts. So when you have 4 minus x equals x squared minus 4x plus 4, you get 0 equals x squared minus 3x. So 0 equals x times x minus 3. So you get x equals 0 and x equals 3. So integral from 0 to 3 of my volume in terms of x, and that is equal to 45 over 4, which I did using my calculator. Okay. All right, one more. So let f of x equal 4 and g of x equal natural log of x plus 1. Let R be the region enclosed by the graphs of f and g and the lines x equal 1 and x equal 4. Region R is the base of a solid whose cross sections perpendicular to the x-axis are squares. What is the volume of the solid? So let's get our axes out. F of x equals 4 is our top line. It's going to be here. Actually, I'm not going to do that in red because red has been a common color for our 3D shape. So do that in green. F of x equals 4. And our other line is ln of x plus 1. Ln of x plus 1. As you can see, there is no region between these two functions because they haven't crossed, and I don't think they do. Region R is the base of a but then we also know region enclosed by the graphs of f and g and the lines x equals 1 and x equals 4. So those lines are going to be right here, x equals 1 and x equals 4. And so as you can see, that creates the base of a region right in here. So that will be the base of our region R. I'm going to erase that so I can draw some cross-sectional squares. So it's going to be like here. It's going to come way up, way up. I drew a really big picture. So here are a few of the square cross sections. Hopefully you can kind of imagine those kind of coming up towards you and see that as a 3D shape. Okay, and we want to know the area of a square. And that is going to be equal to base times height, which are going to be the same in this case. Base equals top minus bottom. So as we can see, here's a base of one of our squares. And top minus bottom is going to be 4 minus ln of x plus 1. Okay, and then the height is also going to be the same thing. So height equals 4 minus ln of x plus 1 as well. So therefore, my area is equal to 4 minus ln of x plus 1 squared. And my volume would be 4 minus ln of x plus 1 quantity squared dx, adding that little bit of depth. And then to sum up all of my 3D shapes, I'm going to take the integral from 1 to 4. And those are my bounds this time because it starts at 1, ends at 4. And then again, I can approximate this using my calculator and I get 23.3816. Okay, and so I want you guys to go ahead and try the other two on this next page as homework. That will be your only homework. And then we are going to go over part 2, which is volume of a solid with square rectangle cross sections perpendicular to the y-axis in class. So don't worry about the worksheet. I want you guys to really focus super hard on the other two problems. I will post the worksheet. And so if you don't watch the video, then you will uselessly do the worksheet. So hopefully you guys watch the video. And again, let me know if you have any questions, come to tutorial. And other than that, have a great day. Thank you for watching.